Hey, hello guys, welcome, Pranakam, Vandanam, Namaskaram. Today we are going to see second part of moving charges and magnetism. Okay, so already we have covered part 1. Now we are going to deal with part 2. Okay, so if you haven't seen part 1, I would suggest you all to see part 1 first before seeing part 2. Okay, because part 1 is very basic thing, that is the foundational level. Then after totally seeing part 1, if you are seeing part 2 now, then this total lesson itself will be very easy. I have discussed everything as much as possible. I have not left any points. Okay, I have not left anything. As much as I can, I have said. Okay, so now we will be proceeding with part 2 itself. Okay, part 2, moving charges and magnetism, that is not required. Okay, so last part, okay, we have completed that magnetic field around a circular loop. Okay, that one we have completed. Now we are going to see the Ampere circuits law. Okay, Ampere circuits law. Okay, what is Ampere circuits law? First, who's Ampere? Who's Ampere? Ampere is the scientist. Okay, he's the scientist whose name has been kept as the SI unit of current, right? Okay, and he's not the one who has found current. Okay, Faraday was the one who has found magnetic field. Well, I don't know what Ampere found, but he's the one who's being kept as the SI unit for current, and very important scientist, that alone I know. Okay, so what he says is you have to take a surface. Okay, you have to take a surface. Okay, for an example, let us take this surface. It need not to be this much irregular. It can be also irregular. Okay, there is no thing like it has to be only irregular. There is no such thing. Okay, and in this surface we are passing current. Okay, like this you are passing current, and the currents are actually flowing. One is flowing in this direction, one is flowing in this direction, one is flowing in this direction, like that. They are flowing in different directions. Okay, so let us take these as those directions. This will be I1, let it be I2, let it be I3, and let it be I4. Okay, so all these are flowing in different directions. First we will be checking how to do their net current. It's very simple. So we all know that current is additive. Just like charge. So what you have to do, you have to add the same direction. Okay, you have to just add the same direction with currents, and you have to subtract it with the opposite directions current. So that means I can say this as, okay, I2 plus I3 plus I4 minus I1 is equal to I net. Okay, so this is something you have to know. Okay, so first we will be checking what is this Ampere circuit law. Something that I have said is some basic things only. Still now we have not yet entered what is Ampere circuit law. Okay, that we will be going. Before that we have to know some few points. That is what I am saying. Okay, so this surface is there, right? This surface is actually what? Amperian surface. Okay, it is I don't know spelling of Amperian surface. P-E-R, okay, Amperian surface or Amperian loop. It's not surface, it is loop. Just like Gaussian surface we have studied in the Gauss law. Okay, where there electric flux, okay, electric flux is equal to 1 by epsilon naught into Q net. Okay, this is what the formula that we have studied over there. Yes, right. So it is very simple. Okay, this total thing, okay, this total concept of electric flux, all those concepts are very similar to the concept that we are about to study in Amperian circuit law. Okay, so before that also we have seen the magnetic field's basic formula, right? What is that basic formula? That is magnetic field is equal to, once again I forgot the formula. Wait, for current. Okay, so for current, how it will be? It will be mu naught square. So here it will be NA R square. Yeah, NA R square. So mu naught NA R square will be the formula. Then what is the very basic formula of magnetic field? From Biot-Savart's law, we have got a formula, right? From Biot-Savart's law, what is that? It is going to be, okay, so magnetic field is equal to mu naught into what? So they have given us ideal sin theta whole divided by, so it will be mu naught by 4 pi into r square, okay, into r square. We have studied over there itself, right, where magnetic field is directly proportional to ideal sin theta, okay, where this theta is, for an example, if this is where the conductor is, okay, then in this conductor the direction of current, and then this length you have to take, okay, then it will be giving you some direction, okay, then it will be a vector quantity, where this will be a vector quantity, so you have to do cross product, then you will be getting sin theta, okay. So here there will be some sort of theta, that theta is what? This theta. All these we have seen over there, right? I'm just giving a small recall, okay. So ampere and loop we are having, so ampere circuit law, current, so yeah, after ampere and loop, now we will be entering into the concept of what is ampere circuit law. What is it? It is note is very important, okay. The line integral, okay, of magnetic field, the line integral of product of magnetic field and ideal and the length, okay, and then the length is equal to mu naught of net current, mu naught of net current. Okay, so if you want, in terms of English sentence, if I can say that, it states, okay, it states that the line integral of, okay, the line integral of B naught, okay, or magnetic field also you can write, okay, B naught, yeah, I'll write it as B vector itself, okay, B vector around a closed path, okay, around a closed path, okay, the closed path is the Amperean surface, okay, closed path is equal to in vacuum, sorry, first in vacuum, oh, in vacuum, okay, in vacuum is equal to the mu naught times of the net current, okay. So this is it, okay, this is what the statement is. And one thing we have to say is that this is actually something that will be happening in the vacuum, okay, in the vacuum, okay. So yeah, we have seen till now this is what the Amperean circuit law is. So where will you be using this formula, and where you will be using the other formulas, like for straight line we have given one formula, right? I will write over here itself. Okay, the first very basic thing is for magnetic field we have given one. I'll write in pink color so that it will be kind of not in pink color or any other color. Okay, this color is equal to K. Okay, K into ideal sin theta whole divided by r square. This is the first formula that we have seen. Then, okay, in a circular coil, what we have seen, magnetic field is equal to mu naught into NIR square whole divided by, okay, whole divided by what? 2 into x square plus r square to the whole power of 3 by 2 is the formula that we have seen. Yes, right? All these formulas we have seen. But I don't know why am I asking yes, right? Somehow no one is going to respond. Neither am I going to, neither can I expect a response because this is not even a live. This is just a video. OMG, something is happening. Okay, and also we have in case of straight line also. Okay, in case of straight line also we have to see. So for a straight line, how it will be? For straight line, actually the formula is very easy. It is in straight line. So how you will be taking it as, you can take it as B is equal to, in denominator 2 pi r will be there, then in the numerator what you, so 2 pi a will be there, which is the length of the conductor, but 2 pi r also you can take, r also you can take as the length of the conductor, then in the numerator mu I, mu naught I. Okay, if you're taking r as the length of the conductor, then okay, because 2 pi r is something that formula we are normally hearing each and everywhere, right? The total circumference of the circle formula is 2 pi r, so you can just relate like that. But r means the length of the conductor. That alone you have to know. Okay, so now what we are going to see is about solenoids. Okay, about solenoid. Okay, so before going into this one, also we will be seeing about toroid, that I have to say. In order to save the time, I have to say only one thing. Solenoid and toroid are same only. They don't have any difference at all. Solenoid will be linear in structure, whereas a toroid will be circular in structure. That's it. Okay. Whereas when you are bending the solenoid, okay, solenoid will be like this. When you are bending the solenoid into like this, okay, just like the tree that we used to draw, right, when we are very small, like that, you can say. So these two are very same, very same. Okay, literally similar. Okay, so I'll first. Okay, so this is negative and then this is positive, right? Now for the purpose to explain, we'll say everything over here. Okay, so it is positive. That means okay, so here how will be the magnetic fields? First they all will be going like this. Okay, inside they all will be going like this. Okay, this is something that you have to know first. Then also magnetic fields will be like this. Okay, also outside also there will be magnetic fields like this. Okay, and also if you just notice, okay, even here also there will be magnetic fields that will be produced. Okay, and also in the top, every curve, okay, for every curve there will be magnetic fields that will be produced as concentric circles. Okay, like that magnetic fields will be produced. Okay, and also one more thing is, here the magnetic field that is produced here and here, right, it will be cancelled like this. Okay, you can cancel them, and also the magnetic field that will be produced here, each and every, see, this magnetic field will be cancelled by this magnetic field will be cancelled by this magnetic field will be cancelled by this magnetic field will be also cancelled by this magnetic field will be also cancelled by this magnetic field will be also cancelled by this magnetic field also will be cancelled by this magnetic field will be also cancelled by this magnetic field. Okay, but some changes are there that we have to see. Okay, so each and every magnetic field that will be produced will be actually cancelled by this opposite magnetic field, because if this is in clockwise direction, if these magnetic fields are in clockwise directions, then the magnetic fields top will be in anti-clockwise directions. So that what will be happening is, each and the effect that is produced by the top magnetic field will be cancelled by the effect that is produced by the magnetic field that is in the bottom. Okay. But one thing to be very accurate, okay, to be very accurate is that we will keep these points. Okay, first we will be giving these points a few names. Okay, let us take that this is 1, this is 2, and then the magnetic field that is in which is drawn like this is there, right? That as 3. Okay. Make sure that you draw like this. Okay, these two will be or should be in opposite direction. Okay, these two should be in opposite direction. Okay. Why am I saying these many okays? Okay. So first, maximum at most, the most highest magnetic field will be in center only. Okay, center only will be there between these coils. Okay, between these successive coils, there will be magnetic field that will be produced. Okay, it will be just going. So it will be very high in this place only. So magnetic field at point 1 will be very high. Okay, it will be very high comparatively to the points that is outside and over here. Okay, then secondly, outside point will be there. Okay, which is B3. Actually, here it will be very negligible. Okay, here it will be there. The magnetic field will be there, but it will be very negligible. Negligible. Then after this we are going to see B2, which is these concentric circles. Okay, they are not that much negligible. Okay, so they are just 0. They are just 0 because here these two are concentric circles, just like that they will cancel. Okay, they are just 0, or also they can be also negligible. You can take them also negligible, but B3 will be comparatively higher than B2. Okay. And also one more thing, that magnetic field is additive. Okay, magnetic field is not additive. Sorry, it is vector quantity. Magnetic field is not additive. Okay, magnetic field is not additive. I'll take this color. Yeah, B net is equal to B vector net is equal to B vector 1 plus B vector 2 plus B vector 3 plus B vector 4 x on how many magnetic fields are there. Okay, so if there are a lot of magnetic fields, it will be just going, so here will be n. Okay, and this positive here, the sign should be positive or negative or what is said by their angles. For an example, if B vector is like this, okay, if B vector is like this, and if B2 vector is like this. Okay, if these two are like this, and they will be having some theta, right? If in case this theta is 0, okay, is 0, then you can just like that you can add them like scalar quantities. If in case theta is 180, okay, if theta is 180 degrees, then what you will be doing? You have to subtract them. Okay, B1 minus B2. Sorry. You should subtract them since they both are in opposite directions. Then if they are in some other angle, then what you have to do? Then B vector 1 plus B vector 2 gives rise to root over modulus of B1 square plus root over modulus of B2 square plus 2AB cos theta is the formula that you have to know. Okay, this is what you have to know. This is something that we have studied already in our class 11th itself, right? But one thing is that we keep on saying this in every part of the class, is that current is not a vector quantity, so that we have to thank current. If in case it were vector, then that's it. Kadam ho gaya. Okay, so this is there. Then we are going to see, yeah, so the magnetic field which is over here, right? The magnetic field that is between these concentric coils is there, right? Those magnetic fields will be, yeah, they will be uniform in nature. They will be uniform in nature. Actually, since they both are they both are actually uniform in nature. Okay, they both are just uniform in nature. You can say them as that is why the reason is they are very strong. Okay, if in case any field, magnetic field or electric field, they both are actually uniform in nature, then we'll be saying that as, then they will be definitely strong only. Okay, they will be strong. I don't know why today I'm not always satisfied with my English. It's very poor. Strong in nature. Okay. Next is, okay, so these all things will be happening. Now we are going to see, this is all in air. Okay, this is all in air. Then with a material in sense what? A medium. Okay, a medium material. Yeah. We will not be using here dielectrics. Okay, we will not be using here dielectrics. We will be using some other materials such as soft iron. Okay, soft iron is an alloy of iron, nickel, and chromium. Okay, of iron, nickel, and chromium. Most used. Okay, most used is soft iron. Soft iron, which is iron, nickel, then chromium. Okay. So this is negative, and then this is positive, right? Okay, so over here I've kept a soft iron. Actually, soft iron will be coiled. For an example, if this is what the soft iron is, okay, if this is what the soft iron material is, then it will be coiled by these coils. Okay, so soft iron, it is a alloy of iron, nickel, and then chromium. So I can draw soft iron like this. It will be coiled, where the magnetic fields that are produced, okay, magnetic fields that are produced will be highly concentrated. Highly concentrated in sense the power of magnetic fields over here will be very strong than here. Okay, I think in my class 10th I have studied that it will be 10 to the power of 6 or 1 lakh times. Okay, or 10 to the power of 6 only I think, or 1 lakh times. Okay, it will be higher. Okay, and also even in fan, okay, the fan that we are seeing, right, it has toroid in it. It has the bend shape of the solenoid. Okay, so yeah, now we are going to see some formulas for this one. Okay, the magnetic field that is over here we are going to see, okay, in with respect to air. No, here I cannot write, here only I have to write. Okay, so it will be in air. Okay, so there will be magnetic fields like this, right? What we are going to see is, we are going to see how will be the magnetic field at inside and outside. Okay, at inside and outside. I'm going to consider what color? Yellow color. Okay, like this we are going to see. So we are going to see the total magnetic field that is in this box. Okay, that is in this box, where in this box is being kept a little bit outside, and also a little bit inside. Okay, so according to nomenclature, okay, what we are going to do, we are going to keep this as A, B, C, and then D. Okay, so we know that the line integral of B dot dl is equal to mu naught times of total current, okay, which is very similar to flux. Okay, electric flux I'm talking. Okay, electric flux is equal to 1 by epsilon naught into q net, where here instead of q net we are having I net, instead of 1 by epsilon we are having mu naught, and instead of electric flux we are having here line integral of magnetic field into length, okay, into the length of the total conductor. Okay, so yeah, coming back to the concept itself, the total magnetic field at this box is B dot dl is equal to, now what we are going to do is we are going to split this into 4, since we are having AB, AD, DC and BC, okay, like that we are having totally 4 different lines, right? So you can say this as AB, so which is going to be B dot dl itself. Here you are supposed to put this naught, okay, here, but here you are not supposed to put this naught, okay. So plus, then AB, sorry, just now we have completed AB, now BC, okay, BC, which is B dot dl, then plus AD, which is going to be B dot dl only, plus then DC is there, so yeah, it is going to be DC, which is, yeah, vector quantity, 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 and here also it is going to be vector quantity. Okay, and also I hope you all can understand what product we are doing. We are doing here dot product. Okay, we are doing here dot product. Okay, so dot product, in sense how it will be changed. It will be changed as, okay, it can be changed as B dl cos theta. Yeah, cos theta. Okay, cos theta. So first is AB. See, AB. So that means this theta is between the magnetic field and in this line. Okay, so this is what the length is and this is what the magnetic field is. What is their direction? So first I will be keeping their directions also. Like this you keep their directions as. Okay, so here these two directions are very same. That means they are 0 degrees. So cos 0 degree is going to be 1. So you can say this as the integral of, okay, the integral of B dot dl, which is A B. Okay, then also plus see, next is BC we are having, right? So BC and then these two are perpendicular to each other. That means they are 90 degrees. So 90 degrees, and then what they are 0. Okay, so cos 0 will be 0 only. Okay, so sorry, cos 90 will be 0. So that means this total term will be 0. And over here, which is AD, okay, AD will be also completely 0 because there also it is perpendicular to each other. Then we are having DC. Here it is what DC. DC is actually 180 degrees, even though it is 180 degrees. Okay, even though it is 180 degrees, which is, but here you have to take B. Okay, you have to take magnetic field. Magnetic field outside this point, outside this solenoid is 0 only, right? So here this total term will be 0 because here magnetic field is 0. So that means every other term, instead of every other term, you are supposed to put 0. Okay. So 0 plus 0 plus 0. Now what you can do is you have to integrate it. AB and then dl, which is B dot dl cos theta. Okay, see, since it is all coils, these all are coils. Here for circles and here for coils, you are not supposed to put this limit, okay, this lower limit and this upper limit, you are not supposed to give it as input. All you have to do is you have to cancel this d and you have to cancel this integration, then it will be B dot dl cos theta is equal to BL. Okay, so like this you have got it. You have got it like this. Now what do you have to do? Still now you have to. Now coming to net current, that means the total current. Okay, so next is I net, the total current. So what is this total current? I net is equal to I n. See, here n represents small n into L. Okay, here n represents small n into L. What is the small n? What is this L? I'll say all those. I net. Okay, because here capital N is equal to small n into L. Okay, ma? Perfect. So, what is this capital N? See, first small n is equal to capital N whole divided by L. Because the small n is actually number of turns per unit length. Okay, number of turns per unit length is what this small n is, and L is the okay, so that is what per unit length you can keep. Over here for this formula, that is what, when it comes to n is equal to nl, okay, n is equal to nl, then how it will be? It will be total number of turns, okay, total number of turns, where L is the total length and n is the total number of turns per unit length. Okay, so that is what I've written over here. So I net is equal to INL. Yeah, I've got this. I net is equal to INL, and also we have another formula, right, which is equal to, yeah, mu naught I net. So I can substitute this over here. Mu naught I net is equal to mu naught I into INL. Yeah, so mu naught I into INL. So I've got this particular formula. Next is what? I'm so sorry that you have heard some external noises. Yeah, I cannot say other than that. I'm so sorry that you had heard some external noises. Here will not come. Okay. Now what you have to do, you have to equate them. Okay, this equation you have got, this equation you have got. All you have to do is you have to equate them. So mu naught I NL is equal to BL, okay, is equal to BL, where this and this can be cancelled out. Then B is equal to, okay, so since this is important, I'll write in another color. Okay, so B is equal to mu naught INL. Okay, so mu naught INL. Okay, so B is equal to mu naught INL. This formula we have got, which is, see, this B is directly proportional to N. Okay, this B is directly proportional to N. This B is directly proportional to also to L. It is also directly proportional. Since mu naught is constant, you cannot take it as. Okay. Next is with respect to medium. All this we have seen is in air. Now with respect to medium. With respect to medium. Okay. So how it will be for now? It will be B is equal to mu naught Ni is the formula. So in medium, okay, this is in air. Okay, this is in air. Okay, then how about in medium? First, what you have to know is in medium there will be a few changes. Okay, that is mu naught will be converted into it's just mu, which is equal to mu naught into mu r. Okay, mu naught into mu r, which is equal to. So now B is equal to mu naught mu r Ni L. L is cancelled, right? So here L will not come. Sorry, I have written over there L. Here L is cancelled. Okay, so here is N is not the subscript. Okay, N is not the subscript. It is number of turns per unit. So yeah, it is total number of turns. N is number of turns per unit length. Yes, no, yeah, this one. So you have got this formula. I will write this also in another color since this is very important. So what you have to put over here? You have to put B is equal to mu r into mu naught Ni. That's it. You have got this one formula. Next is, now also they might ask you another question, which will be, how will be the magnetic field at one end of the conductor? Okay, so one end of the conductor. Oh, one end of the conductor. The magnetic field, it is going to be just half V by 2. Okay, V by 2. That means just divide the total equation by 2 if in case it is kept in a medium. Okay, if in case it is kept in a medium, then you have to divide this equation. If in case it is not kept in medium, and if in case it is in just air, okay, then you have to divide this total equation by 2. So V dash is equal to mu naught In whole divided by 2. Okay, in air. Then how about with in medium? It will be mu naught mu r In whole divided by 2. Okay, so this is what it will be, how it will be. Okay, perfect, right? Okay, next is, after this, what do we have? One graph alone we have to discuss. Space is there, right? Yeah, there is space. What you have to do is you have to consider okay, so you have to consider like this. Okay, so where this is minus L by 2 and this is plus L by 2. Okay, then also, yeah, okay, so this is at one end of the conductor, this is also another end of the conductor. Okay, so from in the very end of the, that means if this was the, so not the conductor, the solenoid. Okay, if this was the starting of the solenoid, so here magnetic will be very less. Exactly in the center, at the center of the total solenoid, it will be very high. Then again in another end, it will be very less. Okay. Then we have to deal. Yeah, I've already said, I think, that this represents what? This represents what? This represents an electric field is actually going inside. This represents an electric field is actually coming in outside. Okay, yes, right? Yes, sir, I have not forgotten correctly. Yeah, so this means it is going inside, and this dot means it is coming outside. Why did I get confusion over that? Very basic. Inside, outside. Okay, then next is be at a point on the infinite straight wire. Yeah, so that means magnetic field at a point, okay, due to, see, this is what the magnetic field, this is what the point is, this is what the straight wire is, and this is actually caused, okay, the magnetic field is actually caused by the straight line or by the straight wire. Okay, well, so this total distance is r. Okay, so this total distance is r, then this is dl, then yeah, this is I, because current is going in this direction only. Then if current is going in this direction, then how it will be? Then the magnetic field will be in this direction. Okay, so this is what the dl is. So what is this dl actually? It is ideal, you have seen, right? Okay, ideal you have seen now, just the length. Okay, it is just the length, one particular length. Okay, only one part only we have seen. Already in the previous video itself, we have derived the total derivation of a this infinitely long straight line. This infinitely, yeah, the magnetic field that is caused by an infinitely long straight line. Okay, that one we have already seen, right? Here also it is going to give you the same formula only. First I'll write the heading. E caused by an infinitely long wire. okay, which is B dot dl is equal to mu naught I net. Okay, next is B integral of, okay, so dl is equal to mu naught I, then dl, okay, is equal to what? Mu naught I. Just net as I've written as I. You can also write it as net, no problem with it. Okay, so till now there is no doubt, right? Just we have integrated it. That's it. This and this will be cancelled. Okay. So here what you have to see is, you have to see this is a circle. Okay, this is what the circle is, and length, this is what the length is, and you have to take this total circle. Okay, because this particular line is what causing this total magnetic effect. Even though you are taking this one point, but even though you are taking only one point, this effect is caused by this total circle only. So what you have to do is, you have to substitute in place of L 2 pi r. So B is equal to mu naught I. Okay, mu naught I whole divided by 2 pi r. Okay, divided by 2 pi r. Yeah. So what you have to do is, we have to I can write this total thing also in terms of k. Okay, because with k now the formula will be a little bit short, right? So divided by k multiplied by k, then B is equal to 2 mu naught I whole divided by, sorry. You can write this total thing as k na k, then this will be 2I by r, and then this is going to be 2I by r. And also this is what the formula that we have got, mu naught I by 2 pi r. I said now mu naught I by 2 pi r. That is what I said, right? That's what even we have got over here. There won't be any difference with when you are using Ampere circuit law and when you are using that formula. Ampere circuit law is very similar to Kirchhoff law, and also it is very similar to the flux, because Kirchhoff law will be used whenever there is a circuit, a very complicated circuit is there, then you will be using Kirchhoff law. Okay, then how about this one? You will be using this one when there is not like a complicated thing. Yeah, you will be also using this one when you are having very complicated, when you are having more than one electric wire which has more than one current, right? See, more than one electric wire, then there will be more than one current flowing. Okay, so this one you will be using. Next is magnetic law. Yeah. Next is toroid. As I said that toroid and solenoid are very same. Okay, toroid and solenoid are very same. Now we are going to just prove it. Okay, so be at different points. Okay, different points on a solenoid. This was asked as question. Okay, this was asked as a question in 12th board examination. I cannot believe that I'm studying 12th. Just a very, that's it. School life itself is about to over, right? Just imagine how many responsibilities we are going to have in our head. In order to make those responsibilities very easy, we are studying. Okay, why am I talking like a boomer? Coming back to the topic. Okay. This is how the toroid will be. It will be just like this coil. Okay, the solenoid will be like this, toroid will be like this. That's it. Okay, then the formula. Okay, so what we are going to do is, we are going to consider a few points. Let me consider this as point P1, this is point P2, this is point P3. So it's going to be, we will write in another color in order to differentiate. I don't know why, but I'm often choosing pink color. Okay. So line integral. This actually normally when you are saying integral is actually of many different types. When you are saying this is just integral, when you are saying like this, it is line integral. Also there are integrals like this. Okay, so yeah, line integral of B dot dl is equal to mu naught I. Okay, mu naught I. Line integral of B dot dl is equal to mu naught I, where B is equal to line integral of in place of I can substitute the formula. In place of I, what I can substitute? In place of, see, this is something we know, right? From what? From Ampere's circuit law, we have studied this formula. Okay, so from this we are going to see this, which is, wait, why am I writing like this? Line integral of B dot dl is equal to mu naught I into n L. Okay, so this formula we know, where in place of L, what we can do, you can substitute the formula of 2 pi r. See, this one totally looks like a circle. Okay, see, this one totally looks like a circle, right? So since this one will be actually circular, I'm not very that much good artist, but this one will be kind of circular only. So you can, this is actually what L is the total length of the total solenoid itself. So your total length of the solenoid will be calculated how? By the circumference, right? So circumference of the circle is 2 pi r. So line integral of this one, this and this will be cancelled out. So it will be just B into 2 pi r is equal to mu naught I n into 2 pi r. Okay. Okay, so this will be cancelled here, this will be also cancelled here, then it will be B is equal to mu naught I n. Okay, so B is equal to mu naught I n. This is what, how it will be over here. Okay, then how will be in the outside? In the outside it will be, okay, so B will be, only this will be changed. Okay, only this will be changed. Rather than that, same like there we have seen, like I said, they are just the same. Outside it is 0, and also at the terminals also it is 0. Terminal sentence over here, here, here. Okay, so here also, here we will take it as yellow color, then B1, okay, then B3, this is B3, B1, okay, which is 0, and here also they are 0. Okay, next is Lorentz force. What is this actually, Lorentz force? What is this total Lorentz force? Lorentz force is the force experienced by a charged particle due to magnetic field. It's the force that is experienced by a magnetic field, which is this beta. Okay, we will keep it like this. Okay, there is this one charged particle. Okay, there is this one charged particle. This is what the direction of magnetic field is, and this is what the direction of the charged particle is about to, when, see, this is where the charged particle is. We will keep it as Q charge. Okay, so this is at rest, not at rest. Okay, it is moving only, but it is moving in some x direction. It is moving in some sort of propagation. It is moving in. Okay, so now this magnetic field is actually hitting this charged particle. Then this is what the movement of the charged particle will be. Okay, this much amount of deviation. Okay, this much amount of deviation is. It is not the deviation, it is just the angle of the propagation of this charged particle, and then this magnetic field. And note, always note this one point, very important point, that, okay, so the force, this Lorentz force will be acting only, will not be acting under these three criteria. Okay, first is the charged particle, okay, before hitting, I'm saying, before hitting, if in case the charged particle is at rest, okay, see, this is where the charged particle is, and this is where the magnetic field is. It is just going, and it is in rest, right? So no matter how much magnetic field you are giving, it will be in rest only. There won't be any thing that will be acting over it. Okay, so at rest, nothing will be happening. Then when the charged particle is moving parallel or anti-parallel, then also nothing will be happening. Okay, nothing will be happening. I don't know from where I'm getting this slang. Okay, so nothing will be happening then also. No, if in case this is how it is moving, and this is how the magnetic field is there, nothing will be happening. If this is how it is moving and this is how it is moving, then also nothing will be happening. One and only if there is some theta degrees, then some sort of change will be happening. And when, okay, note this also, this another point here on it, note. When the charged particle is at motion, then okay, now the magnetic field is there, then it is sitting. But the thing is, this force will be causing this particle to move in a circular way only, one and only in a circular way, because then only the work done will be zero. Okay, work done will be zero because how work done will be zero? It will be zero because the displacement is zero when a body is traveling in a circular path. Okay, in a circular path. So particle is at motion. When a particle is at motion, then when in that time this Lorentz force is acting, then that particle will be moving in circular motion. Then that particle will be moving in circular motion. Okay, my legs are paining. Second seminar of today. Feeling very proud. Till 2 I will be taking. Okay, so particle will be moving in a circular motion when this force is acting on it. With Lorentz force, you'll be completing this total thing. Okay, see here also some statements are there. What are those statements? Proportionalities, just proportionalities we are going to see. Okay, so this magnetic field, so this force is directly proportional to the magnetic field. If magnetic field is very high, then the force that is acting on this particle will be also very high. Then if the charge of the total particle is also very high, then the force will be also very high. Then the velocity of this particle is also very high, and then the force will be also very high. Okay, then sine theta. Okay, sine theta. If this theta is very high now, then that means force is also very high only, because sine theta is directly proportional to theta. Actually, there should be theta only. There should be theta only, but theta is directly proportional to sine theta. So you can write F is directly proportional to sine theta. Whenever you are increasing the value of theta, then automatically sine theta will be also increasing only from minus pi by 2 plus pi by 2. Okay, so when you are combining all these formulas, then what you will be getting? You will be getting a great formula. Okay. Oh gosh. Nothing has gone. Force. Okay. Is directly proportional to dqv sine theta. In order to remove this proportionality, what will be using? You will be using a constant. Force is equal to bqv sine theta, and the constant is k, where this k is actually 1. Okay, k is actually 1, so you need not to write k at all. I don't know from where this voice is also coming. It's very unsimilar, okay, to my original voice. Okay, so this you have got. Next, after this, what you're going to get? Okay, so in terms of vector form, you are going to write. Okay, in terms of vector form, you are going to write. The vector form. B is equal to Q into B cross V. Okay, B cross V. Now you got it. B is equal to Q into B cross V cross. That's it. Very simple, right? So B is equal to Q into B cross into V cross. That's it. Now my backbone is paining. Okay. F is equal to, see, actually it is because this theta is there, right? This theta is the angle between B and V. This is what I've explained over here by my strength. Okay, so that is what I've written over here. Just because when you are multiplying B into V, okay, when you are cross producting B and V, then you'll be getting sin theta. Okay, now what we are going to do is, we are going to see in presence of electric field. This formula is applicable. BQB sin theta is applicable only when electric field is not there. Okay, now in presence of electric field, we are going to see. Presence of electric field. Okay, so the total force net, okay, net force is equal to force of what? Force of that is caused by this magnetic field plus force that is caused by this electric field. Now how it will be? F net is dqv sin theta plus small e into e. Actually, you can also use q into e. I know that, I was the one who have said that. You have to use this q notation for charge when the charge is actually at rest. Okay, and you have to use this notation when the charge is at motion. But here for our, but the thing is, these two magnitude are very same. Okay, are same. So you need not to use your e. Okay, so F net is equal to, take q as common, so q into dv sin theta plus e. Okay, so this b and b can be done what? Cross product. So q into b into v plus e. Okay, e is also what? An electric field. This is in terms of vector product. Okay, in terms of vector. Only one concept is there, that also will be complete today. Okay, now next is okay, so what is next? Okay, next is velocity selection. Velocity selection. What is this velocity selection? See, this is actually the balancing condition. Okay, this is what the balancing condition is. What you have to do is, you have to take, just within 10 minutes the video will be over. Okay, the video will be completed. So this one you have to take. Okay, so you have to, let us keep this as plus. Plus, 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 plus. This will be minus, 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 minus. Okay, this is going to be minus. Then there is also this one oil droplet. Okay, see, what you are going to do is, you are going to make something fly. Okay, you are going to make something fly, float. I don't know why am I dancing. Okay, so this is what the oil droplet is, which is normally considered as the negative. Okay, negative symbol. So first of all, there will be this repulsion, because this is also negative, this is also negative, right? Then there will be attraction, because this is negative, this is positive, and then there will be this force that will be pulling it by, that will be pulled. Okay, that will be pulled by the gravitation. Okay, by the gravitational force. Okay, and also there is this magnetic field. Swank, 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 swank. Okay, so if I draw like this now, then nothing will be clear. So just like this, you draw. Okay, all these indicates the magnetic field. Okay. Now what you are going to do is, you are going to, this is what FB is. Okay, this is something that is caused by the force caused by the magnetic field. Then also there will be this one, okay, that is caused by the electric field. Okay, actually these two will be like this. Okay, so these two will be completely opposite in nature. Not in nature. Okay. See, for balancing condition, what you have to do? Only these two forces are there. Okay, only these two forces are there. So what you have to do? You have to equal them. So that means FB should be equal to FE, where BQV. Okay, BQV is equal to QE. Okay, this one we know, right? We have studied this in that lesson just now. We have studied because sine theta. Here, why sine theta has been neglected? Because see, BQV sine theta is there. Okay, here it is sine 90 degrees. What is sine 90 degrees? Okay, see, this magnetic field, okay, and then this velocity, they both are perpendicular to each other. So that here in this condition, they will be always perpendicular to each other, because magnetic field is going like this and this oil droplet is like this. So then it will be perpendicular to each other. Okay, so then BQV, yeah, then B is equal to E by, yeah, Q and Q can be cancelled. Then it will be E by V, which is, okay, yeah, that's it. We have got this one formula where this is for balancing condition, where the magnetic field should be equal to the ratio of electric field by the velocity. Okay, these two should be equal. That's it. Okay, reconductor, and we are going to end it by a comparison with a bar magnet and a current carrying loop. Okay, single, just one loop. So that is what the last part of this entire lesson is going to be. Okay, so for this concept, what do they ask us? They are asking us the magnetic Lorentz force, okay, for a current carrying conductor. Current carrying conductor. Already we have seen in one of our videos, that is where force, okay, Lorentz force for a single particle. When you are taking a single particle, it is equal to BQV sine theta. Okay, so BQV sine theta, where this theta is the angle between magnetic field and then the velocity. Yes, right, we know all of this. Now what they are asking is, they have kept a conductor. Okay, imagine that this is a conductor. Okay. So this conductor had been kept in a field. Okay. Let us keep like this as the x-axis, z-axis, this as the x-axis, and this as the y-axis. Okay, so let this be the z-axis. Now current is actually passing in this direction. The force, okay, the force that is actually the magnetic force is actually going in this direction only. Okay, and there are electrons in this conductor. Even we know that there will be electrons, right? And then these electrons are having a drift velocity of Vd. Okay, Vd is their drift velocity. Then coming to the length of this total conductor, let that length be L. Okay, and this conductor has no okay, so this conductor is being connected to a battery. See, no byte, no. Okay, so this is what the structure is going to be. Okay. So for a single, for a single electron, what is Lorentz force? Definitely we know that we have already seen this one concept where one electron is there and the magnetic force is there, where this electron is moving with some angle theta, this is there, and this will be making this electron to move in a circular path so that work done will be 0. Yes, right. So here there are like that many electrons. So we cannot calculate for each and every electron in a conductor because there is approximately 10 to the power of 29 electrons in one volume. Okay, in one unit volume, those many electrons are there. So how will you calculate? It's very hard. So that is why we have got a collective formula that we are going to derive it from this formula. Okay, so this is actually used for a single electron. Then how about collectively? That means what you have to do, you have to multiply this total formula with respect to n, where n is the number of electrons in a current carrying conductor. Okay, so I will consider this as small f. Okay, this small f represents the Lorentz force for a single electron. Now what you have to do, now we know this one concept, that is electron density, which is represented as n, is equal to number of electrons in one unit volume. So number of electrons is equal to nV. So you are going to multiply this n over there. Okay. So I have got this. We are going to multiply this n over here. So it will be nV dq sin theta. And also, what is this? This is volume, right? So I can write this in terms of, once again, before doing like this, we will write it in terms of, okay, after multiplying we will write. So for every electron, what it is going to be, let it be capital F. The total magnetic Lorentz force for this conductor is going to be capital F, is equal to BQB sin theta into capital N. BQB into capital N. What is capital N? Capital N is this one, right? So you are going to put this value over there. So force is equal to BQB sin theta into N, which is N into V. Okay, so here volume is there. Volume can be written as area into length. Okay, so we can write that force is equal to BQV. Okay, so this is just going to be N itself. This is going to be A into L sin theta. Okay. So here this Q is what? It is the charge, and I already said that in case of electric, okay, in case of electrodynamics, you should not write as Q, you should write it as E. Okay, so I'm going to convert it into E. Okay, so we know this one mighty formula, that is I is equal to Nai meter. A dog's house. I also said this one shortcut. So you have what? You have N, you have A, you have E, you have velocity. Okay, so from this you can very easily say that force is equal to, instead of all these terms, we are going to write there I. Okay, so force is equal to BIL sin theta. BIA sin theta. So this is how you are going to write it as. Here this velocity is velocity of the charge, right? So which is going to be Vd itself. Okay, so you have got this much. And also you can write it like this in terms of vector quantity. You can write it as how? I said that electron, sorry, not electron, this current is actually a scalar quantity, but when you are writing this current along with the element, that means along with the wire, then it will be a vector quantity. This is also a vector quantity. So you can write that force is equal to, okay, so force, what force? Lorentz force is equal to magnetic field, which is this, into, here cross product only you have to do because of sin theta, into I L. Okay, so this is what you will be getting. Okay, now next what we are going to do. So you all know this. Sin theta na, always you have to write where it will be maximum, where it will be minimum. Maxima and minima you have to represent. Okay. See, sin theta, right? So sin theta will be maximum at 90 degrees. Okay, 90 degrees will be maximum and it will be minimum at 0 degrees. Okay, so that means the angle between magnetic field, which is going to be this one, and then the current, okay, this one, both have to be perpendicular to each other. Okay, then only it will be maximum. And when both the magnetic field and then this current carrying conductor is there, right? When they both are aligned in the same orientation, then they will be in 0 degrees. So that will be the time where this Lorentz force will be minimum. Okay, so we can write it in terms of sentence, that is, magnetic field is great, is high, okay, is high when it is perpendicular to the, force, magnetic force is high when magnetic field is perpendicular to the IL. Okay. Here exactly same thing only, but the thing is when they both are in the same direction. So we are going to write in place of perpendicular. Okay, it is so when here minimum when magnetic field is okay. So magnetic force is minimum when magnetic field is same direction as IL. Okay. Now, next what we are going to see is we are going to see okay. So next is now what we are going to see is we are going to see molar rule. Or also known as okay Fleming's left hand rule. Very simple. You have to take your left hand. Okay. Now after taking your left hand, you have to take only these three fingers and make them perpendicular to each other. Okay, like X, Y and Z axis. Now you have made them perpendicular to each other, right? Now your thumb finger, your thumb represents, then your forefinger represents. At last but not the least, that is your middle finger. Okay, so the middle finger represents. First is this one, okay, first is thumb. So thumb represents the force that is produced by the magnetic field. Okay, so force. Next is the forefinger. Okay, this is what the forefinger is. It is going to be the magnetic field itself. Okay, next is your middle finger, which is this one, which is going to be the direction of current. And when you are writing this, according to the English grammatical rule, what you have to do is, you have to put here if, then. Okay, for every rule, like whichever you are using your hands, right, for that what you have to do is, if thumb finger represents the direction of the force that is produced by the magnetic field, and if the forefinger represents the direction of the magnetic field, then the middle finger will represent the direction of current. This is how we have to write. Okay. And one mnemonics in order to remember this formula is that what you have to do is, see, thumb finger, like this you have to come, which is top, next is the middle, next is the most bottom finger, right? Okay, so here you have to say this as father, mother and child. Okay, so father, mother, child, that's it. Father, mother, child. Okay, so next is the force between there is a force between two infinitely long wires. So you have got two different wires, okay, which are infinitely long. One wire will be giving force on the other wire, okay, and the same will be happening to the vice versa is also applicable. That means okay, so these are two different wires. Okay, and also two different cases are there. First is this wire will be giving some sort of force on this wire, and then this wire will be also giving some sort of force on this wire. Okay, so let this force be force F1 and let this be F2. Okay, and also there is a distance between these two wires. That we will be saying as R. Okay, we will say that as R. Okay, and also there is current flow now. So here also there will be current flow, here also there will be current flow, and so we will be representing this current flow as I1 and then this current flow as I2. Okay, so what are the notations that we want? I have given over here. Now we have to see just the force. Okay, we have to see just the force. Very easy. We are going to do with that. Dark green you will choose. Okay, so force 1. What is this force 1? Actually, this force is produced by the magnetic field. That is, this magnetic field is produced by the current I1, which is in this wire. Okay, so F1 is equal to Bill. Okay, we know Bill sin theta. Okay, so what is Bill? See, over here only, on this only, it is acting, right? So B1 is the thing that is the cause of F1. So B1 you have to write. Okay, I. So I is no. Okay, so then what about I? See, it is actually acting on this wire only, so the I is going to be I2. Okay, and length is common. For here also it is L only, for here also it is L only. Okay, next is length, which is L, and then sine theta. Okay, then you have to write there sine theta. But here you can take that sine theta is equal to 0. So sorry, yeah, sine theta is equal to 0. See, 1, sine theta is equal to 1. That means theta is 90 degrees. Okay, because magnetic field is like this and current is like this. Now, what you are going to do? This is for force 1. Then force 2 is actually same only, but the notation is around different. That is F2 is equal to B2 I1 L. Okay, F2 B1 I1 L. So we know the formula for magnetic field for a uniformly long infinite wire. Okay, see, for a circular loop, this is I'm going to erase. Okay, so that is why I'm not going to write in a very neat way, which is mu naught Ni r square whole divided by 2 pi into x square plus r square to the whole power of 3 by 2. Okay, sorry, just 2. Oh. Okay. I will confirm it. Yeah, it is just the correct formula. Okay, for a circular loop. Then how about for a uniformly lengthy wire? It is going to be mu naught I whole divided by 2 pi r. Okay, so for a lengthy wire it is mu naught I by 2 pi r. Okay, this is also correct. This is for a lengthy wire, this is for a circular loop. So all these we have proved in our previous video, that is why I can remember them. Or else I'll be having amnesia. So here what you'll be doing, F1 is equal to magnetic, this is B1, right? So B1 for a lengthy conductor, this is what you're going to choose. So which is going to be mu naught I1 whole divided by, see, B1 is this one and here you have to put I1 only. Okay, then 2 pi r into I2 into L. Okay, now note this one point, that this is actually length of the conductor. This is not the length. Okay, this is not the length. This is the point. Okay, this is just distance. So you will be writing this as F1 by L. F1 by L is equal to mu naught. Okay, I will write this alone over here. Okay, so F1 by L is equal to mu naught I1 I2 whole divided by 2 pi r. So how about this? See, I don't want to write this again and again and again, so this we are just going to go like that itself. F2 by L is equal to, so in place of B2 you are going to put mu naught I2 into I1 whole divided by 2 pi r. Okay, so you have got this and you have got this. Both are going to be same only. If in case the value of I1 and I2 is same na, and if the length of this conductor and this conductor is same na, then these two are going to be equal. Okay, so now what we are going to do is one note point is there and also one value also we have to remember. So first I'll write the note point. Note. What is the note point? That is, so here this is a conductor and this is also a conductor. Okay, and these two conductors are having current in this same direction only. This is also in this direction, this is also in this direction only. Then will they attract or will they repel each other? That can be the question. Okay, will they attract or will they repel? For my batch, that means when I was studying in 10th standard, they asked me this question. That is, they have given these two wires, and then they have asked whether will that repel or will that attract each other. For 10th standard even they have asked this. So then just imagine how basic will this be. It will attract. Okay. When two current carrying wires are having their current in the same direction, then those two wires will automatically attract each other. When one is actually in the opposite direction, then these two will be repelling each other. Okay. Next is this value you are going to calculate. Okay, the value you are going to calculate when the length is 1 meter, when current is also 1 ampere in both the wires. Then and also the distance between these two wires is also going to be here I have set it as what, as r. Okay, small r. So I will convert this into capital R. Okay, so here this is what you got. Now we are going to calculate one value where current, okay, I1 is equal to I2, which is equal to 1 ampere, then L is equal to R, which is equal to 1 meter. Okay, then in that case force is going to be, okay, so force is equal to 2 into 10 to the power of minus 7, okay, minus 7 Newton per meter. Okay, so force is equal to 2 into 10 to the power of minus 7 Newton per meter. So next is, same direction, they will attract each other, and opposite direction they will repel each other. This is something I already gave. You can also write in terms of watts. Okay, so now the definition is also there. See, it is a constant current carrying. Okay, this value is here, right? That is the value of force when everything is in their unit value. That means when force is, when current is in their unit value, and when. Okay, see, this is the definition with respect to that value, which is 2 into 10 to the power of minus 7 Newton per meter is there, right? So this is what the definition is. That is, see, this is a constant current carrying. Okay, this is a constant current passing through two parallel infinitely long straight wires of negligible cross section, which is kept in air or vacuum at a distance of 1 meter. Okay, that experienced force. Okay, that force that is being experienced by those two wires is what going to be 2 into 10 to the power of minus 7 Newton. Okay, Newton per unit length. Okay, which is 1 Newton per meter. Okay, it is just a constant current. Let's pass it. Okay, so now what we are going to do is we are going to see about horseshoe magnet. Okay, so we are not going to exactly see about horseshoe magnet. Oh, there's a break. Okay, so now what we are going to see is we are going to see current carrying coil placed in a magnetic field. See, listen, this concept is very, very important. Okay, we can give 5 stars for this concept because this concept will be repeat it. Okay, the concept alone I'm saying, the main content, okay, the main context of this content alone will be repeated in the lesson called as EMI, okay, electromagnetic induction, where there what just very basic I'm going to say about that lesson. Yeah, we will be studying, okay, separately very detailedly about that lesson also, but now we will be studying little bit, okay, just basics. That is, okay, so this is a magnet. Here, this is also a magnet. Okay, this is not the diagram that I'm going to draw for this topic. Okay, I'm going to draw it in a very neat way, but we are just checking. Okay, no, I will take another diagram that is very opted for that lesson. See, this is a circular coil. Okay, so this is a circular coil where this coil is being connected to a battery. Okay, so this coil is connected to a battery, and also there is a magnet. Okay, so this one is north, this one is south. You can keep it as. So there will be absolutely what magnetic fields will be there. Yes, right. Okay, so now what we are doing is you have taken this magnet separately. Okay, and you are actually bringing it near, closer to this coil. Okay, in the time what will be happening is this magnetic field will be producing induced EMF. Okay, so the flux will be produced. When induced magnetic flux is being produced, automatically current will be also produced. Okay, so this is what the concept. Okay, literally I've said first part of that lesson in just one single sentence itself in a series way. Okay, so yeah, don't worry, a separate video will make for that also. Okay, now what we are going to do is we are going to see for this one. And also this concept I explained, right? This concept is what actually is there in the generators. Actually, generator it is quite different. There will be two magnets. Okay, one magnet, another magnet. This is north pole. This is south pole. Okay, here there will be solenoids. Okay, like this one solenoid, like this another solenoid, like this also another solenoid will be there. Okay, so this solenoid will be connected. Okay, will be connected like this. Okay, to where? To a place where petrol can be put over there. Okay, you will be pouring petrol, and after that there will be just a wire will be there. With that wire, with an extreme force, will be pulling that wire towards them. Then automatically this will start to rotate. So when it rotates, automatically there will be a change in magnetic field. Change in magnetic field is the primary cause of production of electricity. This concept, okay, this change in magnetic field concept is what now is being used in a wide way all around the world. Okay. Okay. Now coming to our lesson itself, I'm going to take two horseshoe magnets. Okay, these will be producing you radial magnetic field. I will say also what is radial magnetic field. By the way, one small point about radial magnetic field is that it will be very stronger. Okay, radial magnetic field is very stronger than normal magnetic fields. Okay, next, like this, another magnet will be there. Okay, so here north pole is there, here south pole is there. Okay, so there will be one coil, okay, one plate like coil is there. Okay, so a coil like this is over there, and this north pole and the south pole is there. We all know that south pole is positive and north pole is negative. Okay, so there will be magnetic fields. Okay, but this magnetic field is there, right? This magnetic field will be overlapping itself. For an example, if this is one magnetic field, then another magnetic field will be there, then another will be there. Okay, then another will be there, another will be there. Like that, overlapping of magnetic fields will be there. Like this, overlapping of magnetic fields you can very easily see. Okay. Now, because of this magnetic field, there will be toroid. Okay, toroid, there will be force that will be there. Okay, a torque will be produced. Okay, so here one torque will be there, towards this direction one torque will be there. Then towards this direction one torque will be there, and also towards this direction another torque will be also there. Okay, coming to the case of nomenclature, here it is D. Okay, here it is D, here it is C, here it is B, here it is A. Okay, so let this one be. Okay, so let this one be F4. Okay, let this one be F3. Let this one be F1. Let this be F2. Okay, now you can see one common thing, that is this is actually in this direction and this force is also in this direction. Well, this is not, yeah, this is force from D. Okay, so one is like this, another is like this. So this effect can be cancelled out. Okay, this effect can be cancelled out and this effect also can be cancelled out because F1 and F2 are equal but they are in opposite direction. Okay, so F1 is equal to F2. Okay, but they are opposite in direction, so you can just cancel them out. Coming to F4 and F3. Now what we are doing is we are going to find torque. Okay, so torque so torque. First is torque 4 is equal to, torque 4 is very simple. What is the formula of torque first of all? Torque is equal to force into perpendicular distance. Okay, a small twist is what we will be saying as torque. Okay, when there is a force that is acting in a single object in two different objects, okay, and that causes that particular object to rotate, then we will be saying it as torque. Okay, so torque is equal to force into perpendicular distance. Now coming to torque of 4. Okay, that means here one torque will be produced that is equal to force. What is force here? F4 is what they write. So F4 into, what is this perpendicular distance? See, here this distance is there, which we will be taking R. I will also give name for these distances. Well, I'll choose this color. Okay, so let this okay, this has a distance and also this has a distance. Let this be B in length. Okay, so let this be B in length and let this be L in length. Okay, so into what is this? This is what the perpendicular distance is going to be. Okay, so since it is what the perpendicular distance, so you have to write here B. Okay, exactly the same thing is applicable for torque 4 also. So torque 4 is equal to F3. You can see that there is F3 like this. Okay, so F3 into what? Okay, into B. Okay, so torque 4 is there and torque 3. This is torque 3. Okay, so you can see that this force is what different. Okay, this force is what different. Other than that, everything is same. So I'm just going to consider blindly as torque. Okay. So torque is equal to force into distance, which is going to be B. Okay, see the force which is like this, and also over here also there is a force. Yes, right. So, and also I have just now given you the formula that force is equal to BAL for a conductor, not only for a conductor, anything for an object that is more than, what can we say? That is more than one electron, okay, that is more than one charge. Okay, so when you are taking, like let us just take this cross section, okay, just take this much, okay, as a wire. You just take this much as a wire. So in that case, what will be happening? No, you take this as the cross section, okay, as a wire. Then what will be the force? Force is equal to, okay, BIL. Okay, this is what length is L. Now for this cross section, the length is going to be L only. Okay, L into, okay, torque is equal to BI into, what is L into B? Okay, what is L? This is what L, okay, and this is what B, which is equal to area. So BIA. Okay, and also this will not be just one rectangular coil. Okay, there will be more than one rectangular coil. That means here like this, still another will be there. Okay, like this, still another will be there. Okay, like this, still another will be there. Like this, it will be successive, successive, successive. Okay, so for that, what you have to do is, this is for just one. Okay, for one loop. But in the case of more than one loop, okay, in the case of more than one loop, it is not like that. You have to multiply over here number of loops. So we will be taking number of loops as n. Okay, so T is equal to, I will take this color. Okay, so torque is equal to BINA. You just take it as BINA, which is known as BNA. You take it as BNA. So torque is equal to BNA. Okay. Now what we are going to see is, we are going to see tangential galvanometer, or also known as just, okay, moving coil galvanometer. Okay, so moving coil galvanometer. What is this moving coil galvanometer? Moving coil galvanometer is actually also known as tangential galvanometer. Okay, so how this is known as tangential galvanometer? No, there is no how at all. This is just the other name. So actually the primary role of a galvanometer is very simple, that is to detect, okay, which color? This color. Okay, this is used to detect current. Okay, this is just used to detect the current. Okay, so this galvanometer will be like this. It will be just like this much in size. Okay, so like this. Well, this is not the actual size. The actual size will be around this much will be. Okay, so we take this as the galvanometer. Okay, it will be having readings over here. And also there will be one arrow mark which will be pointing towards, like, it will be straight line. Okay, it will be perpendicular to the x-axis if you draw an x-axis. Okay, so this indicates, when it is perpendicular, then that indicates that current is equal to 0. Yeah, I net you can take. No, just I net will not come. Okay, I is equal to 0. When there is some sort of deflection, when it is like this or when it is like this, okay, when there is a deflection, it depends upon the direction of the current, okay, like this or this. Okay, so whenever there is a deflection, well, let this be theta. Okay, let this be theta. Then that means current is not equal to 0 when there is a deflection, when there is theta. I'll erase this also because this is just some basic concepts that you have to know. And also we can say that when this deflection is very high, you can say that it is directly proportional to the current. Okay, so when deflection is very high, it is directly proportional to the current. And in order to remove that proportionality, you can say that I is equal to g theta. Okay, this is what we are going to prove over here. This is what just now I said within some points, right, within some statements. So that is what we are going to see. Okay, so this is a surface. Okay, so over here, okay, two horseshoe magnets are there. Like this, one horseshoe magnet is there, and also like this, another horseshoe magnet is there. And okay, over here you can see one small wire will be there. Okay, one small wire will be there, and also there will be a coil. Okay, there will be coil. Successive coils. And also in between these coils, okay, when you are talking about in between these coils, there will be a material. Okay, so in this area there will be a material called as soft iron. Very very important in this total electricity is actually two different concepts. Okay, two different materials, that is going to be dielectrics, and another is this soft iron. Okay, well, dielectrics is more important than the soft iron. It is just a material. Okay, but dielectrics we are having a lot of concepts. Okay, so like this only it will be. Okay, over here one string will be there. Okay, and one point that to be noted is the string, when you compare, just compare the thickness of here. Okay, this thickness here, it will be very thick, it will be highly thick. Okay, whatever, the same material only is used also here, but the thickness alone, if you are comparing, it will be very thick, but here this string will not be that thick. Okay. Just look how thin it is. Okay, how thin. I don't even know that whether camera can look at this or not. Okay, that much thin it is, so a little bit bigger we will draw. Okay, so this is actually known as hair string. Yeah, hair spring, not string. Okay, hair spring. Okay, and these two materials, this is also, okay, this is also is made up of phosphobronze, and also this is also made up of phosphobronze. Okay, and over here it is actually known as North Pole, and over here it is actually known as South Pole. These two are different poles. Okay.